Because we live in a three-dimensional world, we are concerned with objects having depth or height, as well as length and width. If a given object has a closed, solid form, oftentimes we become primarily concerned with the space it will occupy. If, however, the object is a container for liquids or other materials, then we are more often concerned with its capacity. Such a property of an object is referred to as its volume. The volume of a geometric solid may be further defined as the number of cubic units of a given kind which a solid contains. The question, of course, is how many cubic units does it take to make up the solid? This is true regardless of the shape of the solid under consideration. When we studied prisms and cylinders, we found that the volume could be obtained by multiplying the number of area units in the base by the number of linear units in the height, provided, of course, we used the same linear unit in all our measurements. In a prism, the number of cubic units is computed with the formula V equals BH. The volume of a cylinder is obtained with the formula V equals pi r squared h. In each formula, the same principle is applied. The volume of either the prism or the cylinder is equal to the product of the number of area units in its base times the number of linear units in its height. Now let's see if there's any relationship between these geometric solids, the prism and the cylinder, and these, the pyramid and the cone. For this observation, let's compare a pyramid with a prism, having the same measurements for base and height. First of all, we need to remember that a prism which has a rectangle for a base is a special kind of prism, a rectangular prism. Similarly, a pyramid whose base is a rectangle is called a rectangular pyramid. The shape of such a pyramid is largely determined by the shape of its base. The faces of a pyramid are triangles, all of which meet at a given point called the vertex. The dimension we call height is measured from the vertex along a line perpendicular to the base. Once we know the number of linear units in the height and the number of area units in the base, we then can apply the formula V equals BH. But obviously, the capacity of the prism and that of the pyramid are not the same. The volume of the pyramid is less than that of the prism. We can see this, but now we need to know how much. Perhaps a formula for finding the volume can be developed. How many pyramids of sand will it take to fill the prism? 1, 2, 3. The volume of a prism is 3 times that of a pyramid having an equal base and height. We have now established a meaningful relationship between these two geometric solids. Because we know the formula for finding the volume of the prism, we can now determine a formula for finding the volume of a pyramid. V equals 1/3 the product of the base times the height. A simple illustration of how such a formula could be used in modern industry is that of a box designer who was given the job of creating a new popcorn box, one that would have 1/3 the volume of the box ordinarily used. He could design another prism shape actually 1/3 the size of the original box. But the shape and form of such a change might not be pleasing to the eye of the customer. It looks too much like what it is, 1/3 the original amount. If, however, a pyramidal box is used, the effect is that of an optical illusion. The customer thinks he's getting more than he actually does. There's that same familiar opening at the top and the same measurement in height. But we know, as did the designer, that according to the formula, V equals 1/3 BH. There are, however, many objects called pyramids whose bases are not rectangles. For example, this pyramid is called a triangular pyramid because its base is a triangle. A square pyramid would have for its base a square. The base of a pentagonal pyramid is 5-sided, a pentagon. A 6-sided pyramid, a hexagonal pyramid, is so called because its base is a hexagon. The volume of any of these pyramids can be computed if we know the area of the base and the dimension we call height. By observing once more a rectangular pyramid whose volume is obtained with the formula V equals 1/3 BH, we find that if we bisect the rectangular base, we form 2 triangular bases, hence 2 triangular pyramids. The height remains the same, but the area of each triangular base is 1/2 that of the rectangular base. The same formula applies in finding the volume of the halves as in finding the volume of the whole. V equals 1/3 BH, even though the bases to which we refer now are the triangular bases B1 and B2. Now we have a key for finding the volume of any pyramid, regardless of its shape or size. For those pyramids having 4 or more sides, we simply divide them into triangular pyramids. We use the same formula in finding the volume of any triangular pyramid regardless of its size. V equals 1/3 BH. So, to find the total volume of the original pyramid, we simply add the volumes of the parts. For example, if we take a hexagonal pyramid, a pyramid with 6 lateral faces, and divide the base into 4 triangles, we then can determine the number of area units in each base by using the formula for finding the area of a triangle. Then we multiply the area units in each base by the height. We divide these results by 3, add them together, and we have the volume of the whole, the hexagonal pyramid with which we started. The one thing we need to remember is this: the volume of any pyramid is equal to 1/3 the product of its base and height. V equals 1/3 BH. As the number of lateral faces of a pyramid increases, notice what seems to be happening to the figure. More and more, our pyramid begins to look like a cone, doesn't it? If our figure actually becomes a cone, then the question arises, how do we find its volume? Does the same relationship exist between a cone and a cylinder as existed between a prism and a pyramid? Let's conduct another experiment. As we did before with the pyramid and the prism, let's compare the volume of a cone with the volume of a cylinder having the same size base and the same linear measurement for height. By filling the cone with colored sand and pouring this into the cylinder-shaped container, we quickly determine how many cones it will take to fill it. 3 cones are necessary to fill the cylinder-shaped container. Therefore, we can make the following deduction. Since the formula for finding the volume of a cylinder is stated as V equals pi r squared h, then the formula for finding the volume of a cone can be stated as V equals 1/3 pi r squared h. This formula can be applied to a cone of any size and is used many times in our present scientific world. For example, it's very important to know the exact volume of the nose cone of a rocket. A certain capacity is needed to carry instruments which record scientific data during the flight through space. And yet, size itself is always critical. Weight must be kept to a minimum. To determine capacity, the engineers who work on a nose cone use the same formula the student uses in the classroom. V equals 1/3 pi r squared h. We should remember that pi can be stated as 3.14 or 3 1/7 or 22/7. To make use of our formula, let's find the volume of a nose cone whose diameter is 3 feet or whose radius is 1 1/2 feet, or simply 3/2 of a foot. The height of the cone is 7 feet. Using our formula, we find that the volume of the cone is 1/3 times 22/7 times 3/2 times 3/2 times 7 cubic feet. Or 33/2, or 16 1/2 cubic feet. A nose cone may be used to help launch another man-made geometric solid, a satellite, in the shape of a sphere, the type of solid whose surface at every point is equidistant from its center. The line from the center to the surface is known as the radius. Such a line might extend from the center to any given point on the surface area. A straight line extending from a point on the surface through the center to another point on the surface is a diameter of the sphere. A circular line having the same diameter and radius as the sphere is called a great circle. To develop a formula for finding the volume of a sphere, let's remove one part and divide that part into a number of small pyramid-shaped pieces. The vertex of each pyramid is, of course, the center of the sphere. The base of each pyramid is a minute portion of the surface. Even though part of a curved surface, the small base areas in each of these pyramids may be thought of as polygons or squares. In this case, the height of each pyramid, or h, is the radius of the sphere, or r. The base of each pyramid, designated here as b, is actually a part of the surface of our sphere, or s. The pyramid volume formula could be applied to each of these small sections. And when the sum of the volumes of all the pyramids for the entire sphere were added together, we would have an amount equal to the volume of the sphere. This, then, is the formula. the volume of the sphere is equal to 1/3 radius times the surface area of the sphere. Or, more simply, V equals 1/3 RS, S representing the total surface area. We also know that the surface area of a sphere is 4 times the area of its great circle and can be expressed as 4 pi r squared. Simplified, the formula for finding the volume of a sphere now reads V equals 1/3 r times 4 pi r squared, or 4/3 pi r cubed. When men work with geometric solids, not only must measurements be taken, but calculations must be made, carefully and accurately, with the proper use of proven formulas. In the future, men may find new uses for the shapes themselves, but the mathematical laws for finding their volumes will still apply.